I think we should start. So welcome everybody. Thank you for joining. This session is going to be all about what data science is. We're going to have an introduction and also a interactive workshop. So for today's speakers, my name is Mila. I'm an analytics implementation lead. We have Dev, Audrey, and Hannah online as well. I'll ask them to introduce themselves in a bit. And we all work at Xero. Xero has quite a lot of data roles. There's data analysts, there's data scientists, and a whole lot of other technical roles that work around Xero's data. So in today's presentation, it's just going to give a perspective from ourselves, and we hope that you enjoy it. Just a bit of housekeeping rules. In the chat, I've put a link into for people to send their questions through Slido. I'll try and find a time between the presentation sections to check in there to see what's happening. So Slido lets you post and I think upvote questions anonymously. If you do though want to just ask directly in the chat, then just feel free to do that. So yeah, like I said, my name is Mila. I've been at Xero for I think about 6 months now, and I started doing data science about 4 years ago, and it was mostly because I love telling stories using data. So it's really awesome to do a profession which lets me do a bit of coding and storytelling at the same time. Dev, do you want to introduce yourself?
Yep. Hi, my name is Devaki. I graduated with engineering from the University of Auckland at the end of last year, and I've been with Xero since February of this year as a data graduate. And that's my dog Ruby. It's her birthday today, actually. So yeah.
Hi, I'm Audrey. I am a graduate developer. I also graduated last year, and now I'm a grad developer at Xero.
Hi, I'm Hannah. I'm one of the data scientists here at Xero. I've been at Xero for 4 years, and I currently do a lot of work in the marketing space.
Cool. So for today's agenda, we're going to talk a little bit more about what data science is, and then we have a few points around what data scientists do and everyday kind of things, the different skills that we use, and then the way that we kind of the workflow that we follow to complete some work. Audrey and Dev are also going to give their perspective on being a graduate and joining Xero. And then we're going to have Hannah take us through the interactive workshop. So just as a note, this is from our own perspectives about what data science is. There's a lot of academic research and a lot of work being done within the academic field for data science that is really, really important, and it influences a lot of things that we do within the industry. But today's session is going to be mostly focused on what the experience is like for data scientists working within businesses. Yeah, so let's get into it. So the purpose of data science is to find patterns in data and use these patterns to understand the world and make predictions about it. To do this, we use methods from statistics, computer science, business, and or product knowledge. What this means is that a data scientist is somebody that writes code, analyzes data, and also guides the decision making that the business has. Data science is really quite a recent field, and it wasn't until about 10 years ago, so around 2010, that it really started to stand its own ground as its own field rather than a subfield of statistics or computer science. So I think it's quite interesting to look back at the brief history of data science, because you'll start to see that there's quite a lot of things going on, and that's why when you search up data science, or if you have a conversation with different data scientists, there's a lot of mixed experiences and kind of roots of where everything comes from. So overwhelming little slide about everything that happens. So in 1996, it was the first time that the term data science was used. And at this time, fields like statistics and data mining became a lot more impactful thanks to personal computers, databases, and spreadsheet technology. In the 90s, people were thinking a lot about kind of applying their knowledge and assuming what people wanted. But marketing companies and a few product companies started to shift their thinking. So they were trying to collect as much data as they could and use statistics and spreadsheets and databases to create like targeted campaigns to drive better competitiveness in sales. This was quite different at the time, but it was due to like our technology improving. Then in about 2000s, between like 2000 and 2010, there's a whole load of stuff that happened for data science. So the internet was booming and there was more information being created than ever before, a lot more people being connected digitally than ever before. And this was like kind of the boom of digital data. Companies like Microsoft, Amazon, and Google were fiercely competing at this time to create to have web dominance around the internet, and data was seriously like the like the root of their success. So the more that they could collect and understand about what customers were doing with their platforms, the more that they could predict future needs and anticipate those customer needs. So with that, they also started to develop new technology to process the data and to store it. So cloud computing and cloud storage came to exist around this time. And what this meant is that it became so much more accessible for individuals and small businesses to be able to afford this technology, to be able to afford to process large amounts of data and do their own analysis on it. During this time, companies like Facebook, a lot of the big enterprise companies that we have now, we're really proving the success of having collecting a lot of data and applying that data-driven thinking in their companies instead of the knowledge-driven thinking. So a lot of companies around this time were also thinking, okay, we've got to jump onto this bandwagon and start to collect as much data as we can. Obviously, if you collect data, you need somebody that can process the data. So they were hiring statisticians, computer scientists, anybody that said that they could do something with data, they called them a data scientist, or they called themselves data scientists. So around 2010, what a data scientist did was very blurred. It's literally like anything that had to do with data, you could say that you're a data scientist. So nowadays, when it comes to 2020, there's a new wave of data scientists coming into the field that are actually training at universities or in some other ways to have actual data science education. And that's pretty exciting. The field itself is becoming a lot more mature. So we're seeing a lot more specialization in there. You don't have like the scenario that you can be a data scientist and do whatever in it. You could be a lot more specific about what kind of data scientist you want to do or have more of a focus in your work. Data scientists like to predict the future, and like what I think could happen in the future for data science is this is just a guess, you know. I think in the future what will happen is that data literacy and the ability to do basic analysis is going to become very important for all roles, no matter if you're a technical role or not. And with future data scientists, we're probably going to spend more of our time solving complex and more interesting and fun problems. So yeah, but for today's data scientists, essentially you have kind of 3 different types of, I don't know, specializations that you could do. So as a data scientist, you're still going to have the same core skills, so it'd be coding, statistics, and some business knowledge, but you can also do a bit more specialization. So here I have 3 types of specializations, and underneath is the type of job role that you can search for. So you could be an AI engineer that is in a data specialized team that focuses on developing artificial intelligence applications and products. You can also be a full stack data scientist, which means that you're quite a generalist across your skills, and be part of a product team to help them. You're essentially their data specialist within the team, and you help them find and understand patterns in customer behavior and optimize the products. You can also be part of a marketing and sales team as maybe a marketing analyst or a data scientist, where you're uncovering more of the human behavior and predicting what people are going to do, and essentially find that competitive edge. There's probably a whole lot of more things or specializations. And what's kind of fun about New Zealand and Australian markets is that in most data science jobs, you're going to probably be a full stack data scientist, which means that you're going to cover a lot of different areas of data science and a lot of different applications. Overseas in US, Europe, Asia, there the field is a lot more mature and you have kind of more freedom to choose a specialization. So it's more likely that overseas you can specialize a lot more specifically about what you want to do. But New Zealand's most data scientists are able to kind of jump between different roles and do anything, which I think is actually an advantage. So that's what data science is, very brief. We'll talk a little bit more about the different skills we have. So I'm gonna hand it over to Dev.
Yeah, so there are many key skills that data scientists practice on a daily basis, and they can kind of be grouped into 2 different categories. We've got the technical skills, and then we've got the core competencies, or soft skills as people like to call them. Before I start on these technical skills, just a disclaimer, this isn't something that you would be expected to know coming into the industry. This is just stuff that you might be exposed to in your first year as a data scientist. And the idea of less is more is really relevant here. We aim to use these tools very minimalistically in order to answer our questions. And anything more would be out of curiosity rather than necessity. So it's not important to know everything, and a little bit of exposure to these skills goes a very long way. So as a data scientist, programming is something that you might end up doing on a daily basis. Programming is used in many of the steps of the data science process, from querying a database through to exploring and modeling the data and producing visualizations. And Python and R are very widely used in the data science community, since they are free and they're both open source as well. And they both have many different packages and libraries as part of them. And this makes life a lot easier as you don't have to code things from scratch. And these libraries are forever growing, and Hannah will demonstrate that in her workshop. SQL is also very popular for creating and querying databases in order to actually have data to model. Data visualization is also very important in the field of data science. It allows us to communicate our insights more efficiently to people that might not be from a technical background, and it gives facts and figures to just numbers, and it just gives it more meaning. There are many different tools that you might come across within the industry, such as Power BI or Tableau or MicroStrategy, or you might end up making your own visualizations within R or Python or MATLAB as well. Another thing you might exercise as a data scientist is your statistical knowledge. Stat skills are used to carry out analysis and exploration on the data and identify patterns within the data. And we call upon the stats knowledge to understand the significance and the performance of many of the models that we create, so that we can back the results that we're getting. Although we have all of these amazing libraries at hand that can do a lot of the heavy lifting for us, stats knowledge really helps us to understand where and how to actually use these tools appropriately, and it's really the backbone behind all of these algorithms too. There are many
Yeah.
different machine... Oh, is that
Sorry,
Mila?
sorry, continue.
Okay. There are many different machine learning algorithms out there as well, and data scientists really rely on their understanding of these algorithms in relation to the problem context to decide which ones are actually appropriate to use. And again, there's many tools out there such as scikit-learn and TensorFlow that we can use to do this. Again, don't go home and stress about learning these tools. I haven't used TensorFlow myself, and it's more up there for curiosity rather than actually learning it. I'll pass this on to Mila now.
Cool, thank you so much. So just like a thing about the technical skills is that you really need to just pick up the skills that you need to solve the problem. So once you start working in a new company, or you want to start working on some data science tutorials at home, you just start to pick up those skills that you really need. You don't have to go and like learn everything on this list straight away and then start to find the problems. It's just drive your curiosity first, and you'll see what you need out of it. So the soft skills are really important. That I think maybe is even the skills that you can start practicing and harvesting right now, even without needing to learn a lot of the coding skills or statistical skills. So when we call like soft skills, when I was at studying computer science at Victoria, they said like soft skills is essentially all of the other skills that don't have to do with computer science or coding. And that felt really vague and daunting to me, because it felt like a lot of other skills. But it turns out, I don't know, I don't like the term soft skills, because I think these are actually very hard skills. And these are the skills that will probably, you'll start to work on them now, and you'll continue developing them throughout your career. So these skills are a lot about communication and effectively making sure that other people understand the worth of your work. So some of the soft skills or hard skills that data scientists need to have is scoping the problem and asking questions. This is extremely important. You need to be able to listen and understand what the problem is, and ask any other questions that will help you understand the problem better. The second one, or the second two, is storytelling, reporting, and presenting. A lot of the time when you're working in a company or in a team, you're probably going to be the only data specialist in that team. So you need to tell them essentially a story from A to B about how they can understand the data that you're working with, or the insight that you've found. Storytelling is an amazing tool that that can be, you know, you can pick it up through theater work, through like reading books, anything. Like, I think everybody can be a really great storyteller, and it's a very transferable skill into your data science career as well. With your work, yes, you're going to do a lot of coding, or a lot of talking and coding. You're also going to have to do reports. You will need to have writing skills to clearly explain the work that you've done, and probably more importantly, clearly communicate the key takeaways or insights from your analysis. Presenting is another skill that you shouldn't be afraid of. It's just another communication skill, where sometimes you might be presenting your insight to a group of people that have no idea about data science. They don't understand anything about statistics, but they want to make the best decision possible. And you need to be there to clearly communicate to them what is the data telling us? What can we learn from it? So yeah, the last one is teamwork. At university, my experience was that sometimes, well, a lot of the time there was a lot of assignments that I did by myself, and that isn't the reality once you start working in a business. So when you join a team in a company, you're all going to be working more or less on the same problem. As a data scientist in that team, you're going to be trying to solve that problem from the data science perspective. So you're going to try and leverage as much of the data that you have to answer that problem. So you really need to start working on your team working skills and learning more about the different types of roles that you might be working with, which could be non-technical roles as well. But it's a lot of fun because you start to collaborate together and you'll see that the problem can be solved in so many different ways. And it's that magical synergy of everybody having that input that makes it really rewarding to work. Cool. So the next section that we're going to do is talk about the typical workflow for a data scientist. So it's quite, there's a very common misconception that when we talk about data science work, that it's very closely coupled with doing a lot of machine learning work. But that is kind of true. It's very unlikely that a data scientist would actually jump straight into doing any machine learning applications. What happens is that we tend to follow quite a few steps before we even reach any ML or AI work. So as you can see on the screen I'm presenting, there's this hierarchy, data science hierarchy of needs. And I have, I can share this article from Hacker News about it more because it's really quite interesting, or just search it online. It's quite a popular article. It essentially describes like the a way to think about the workflow for a data scientist or for any analysis. So you have to satisfy the layer below in order to start working on the layer above. So we can't just start working on ML stuff without satisfying all of those layers below in that specific order. So one of the first things that we start doing is problem scoping and investigation. So this means that we're talking a lot. We're in conversations with our team members, with our clients, our customers, to understand from their perspective what's happening. At this point, it's really, really important that we also get an idea of what might be required to answer that problem. So sometimes a product owner might come to me to say that I need to build a dashboard or a spreadsheet that has like 50 million columns in it, that has like rainbow crazy colored cells in it. And at this point, I don't just jump into straight building that dashboard. I sit down and have a conversation with them. So I try and understand, what are they trying to solve? What's the problem? What's the decision they're trying to make? This is extremely important to do this before we sit down at our computer and do anything else. After that, we do data collection. If we don't have any data to work with, we can't do our analysis. Usually what this means is that we go and explore in our database or a data warehouse or a data lake or somewhere where the company's data is stored to understand what data is available that we could probably use to investigate the problem. After that, we start querying it. So we start playing around with the data, trying to get a data set for us to do our analysis. Then we get to this cleaning and formatting stage. I think if you jump into Twitter and look at what some of the data scientists complain about the most, it would probably be about how much time they spend cleaning and formatting the data. What this step is about is that we need to make sure that the data set we're using doesn't have anything that we might not expect to have in it. So there's no missing values. All of the strings, number fields, everything is consistent in the way that we need, like in the right format that we need for analysis. We'll also start shaping it a little bit differently. So if the original data set was like in a really long format, we might want to pivot it so that it's in a really long format. So we are trying to manipulate this data that we originally got so that it fits better for our analysis. At this point, we also start to explore the data a little bit. So we're trying to learn about kind of the nature of it. What does it have in it? Maybe we'll plot out some basic things. We'll look at some example rows in the data to understand like what kind of values can exist in the data and just get familiar with it. it's only after this amount of steps that we start to think, okay, I'm going to start applying some statistical models to this, or some very simple machine learning models to this to help me answer the question better. Then if we are still not done with answering the problem, we can go further by trying to predict what could happen in the next 6 to 12 months with the data if we find a pattern. And if we still haven't found what we're looking for, we can go deeper into creating some neural nets or some more sophisticated AI applications for the data. Like Dev said, we don't go all the way to using deep AI applications for all of our work. Like we have to do the minimum that's required to answer the problem. So that doesn't mean that we always use ML or AI in our applications. And that's totally fine and normal. A good data scientist knows when they need to stop working and when kind of the value for the amount of input that they, or the amount of time that they'll spend working on the problem starts to outweigh each other. Hope that makes sense. Cool. So the next bit is I'm going to hand over to our graduates again, and they're going to tell us about their experience.
Here's some relevant memes for data science that I thought you guys might appreciate. So if we flick on to the next slide, me and Audrey will just be talking you through our experiences at university versus in the workplace. So a little bit of background about what I studied. I studied engineering under a specialization called engineering science. This was like a mixture of operations research and optimization, as well as mathematical modeling, as well as a bit of data science. It was all a bit of a jumble. And I was able to take quite a few elective subjects as part of this degree. So within my last 2 years, I kind of tailored this towards data analytics and data science a little bit more. And comparing this to work, at the moment I'm working as a data analyst as part of my first rotation of the grad program. And the work that I do on a daily basis is querying databases using SQL and then producing visualizations and dashboards for other teams within Xero for them to make decisions. A few key differences that I found between uni versus work was the fact that at university we had all of these static assignments with rigid problems, and coming into the workforce, these problems and questions are coming from real people, and real people always have changing needs and changing requirements. So I've learned a lot about flexibility within my mindset, and also the way that you frame your code plans so that things can be adjusted quite easily. Another thing that I didn't have any experience working with was querying large databases and large data warehouses. And at uni, all of my queries at least would take a few seconds to run because we were querying such small data sets, whereas coming into the workplace, all of my queries were just being aborted because they were too long and they were just not efficient enough. So I've really learned how to write more efficient queries, and yeah, so that's been a big difference. Another thing that I was really worried about coming into the workforce was having to know everything. I had definitely forgotten a lot of my key skills from uni over the summer break. And at university, for every assignment, Stack Overflow was my best friend. Like Stack Overflow was what I resorted to for every single question, or lecturers or peers and that kind of thing. But I just wasn't sure whether it was socially acceptable to Google things at work. And it is, it really is. I Google things all the time, and talking to other analysts and scientists and developers, they do too. So don't feel like you have to know everything, because work is like an open book test almost, and you're not expected to be a dictionary. So that's something that was really good and comforting to realize. But yeah, I can imagine you being a little bit scared or nervous about the work experience being, that you have to know everything, and that's just not the case. Yep, and I'll pass it on to Audrey now.
Hello. So I'm just going to talk about more generally the difference I found between university and work. So I think one of the biggest differences in university is that you deal with a lot of hypothetical problems, and there's a lot of theory, but I think because of the problems you deal with are hypothetical, it's quite confusing to understand how the theory you're learning is applicable to what you're doing. But I think in work, because you're working on real problems and you do a lot more hands-on work, you get a better understanding of how the theory you learned at university is important and why you need to know that, which I find really good for my own learning. Another thing is that you start from scratch usually when you get assignments and projects, which is pretty scary because you make decisions by yourself a lot. While at work, there's a lot of existing infrastructure and setup that you have to often adapt to, which is also scary because you can break things and you touch other people's stuff. One of my favorite things about work is the fact that there's a consistent work schedule. I know when I was at uni, I would get like really stressed at times and do a lot of work at really concentrated periods of time and then just worry about the work that I needed to do other times. But I feel like with work, because it's like a schedule, I can just relax at the end of the day, which is really nice. As Mila said, a main difference I found with work as well is that you get to talk to a lot of different people, because even if the work that you're doing is only with like one person, which I'm doing in the project I'm working on, it still influences and relies on information that a lot of work that other people have done. And so you get exposed to a larger variety of people. And then I'll talk to you guys about the Xero. So if you guys are interested in becoming a Xero, there's two main streams. So there's a graduate program, which me and Dev are a part of currently. And there's three main streams for the graduate program, which is becoming a developer, becoming a security engineer, and an infrastructure engineer. These applications close on the 31st of July. They're a year-long program, but at the end of the year, you get a permanent role at Xero, so you don't have to worry about not having a job. They're rotation-based, so it's split up into 4 different rotations, so you get to try different things. So if you want to be a developer, but you want to have a taste of data, you can take one of your rotations can be in data, which is really good because it exposes you to a lot of different flavors of Xero. Another way to get into Xero are through internships. So our internships are run through Summer of Tech, which is just basically an online intern program. And they run from November to February. And on to Hannah for her workshop.
Just before we go in there, I'm just going to answer a quick question on Slido. The question is essentially like, how do you communicate a data story accurately, and how do you have enough certainty that you're doing things correctly? I guess the nature of our work is that we are communicators of what the data is telling us. So we apply different techniques to learn more about what's happening in the data, so the different patterns, and trying to understand how, like, what the world is describing. And then we communicate that to our teams, clients, and customers. So when I was studying as a data scientist, I was super nervous to like share any kind of insight because I thought I needed to check it like 100 million different ways to make sure that I was concluding to the right thing. So for example, if it's like an A/B test that we're running on the website, and I needed to conclude that the cohort B, so like our new shiny website variation, was actually a much better experience for people, I would do like all sorts of things to try and figure out if that was actually correct. There's always going to be uncertainty though, and you don't have to be, it's wrong for people to assume that you're going to be like, I don't know, like a calculator or a computer or something that's always going to output the right data information. The best that you can do is just provide the clearest information you can, making it clear about the assumptions that you've made or any kind of uncertainties that you have about the data. It's not on you if like things go wrong. It's probably a very toxic working culture that would say the otherwise. Most of the companies I worked in are very supportive if I go back and being like, hey, I've learned something more about this, and I think I want to amend my conclusion in there. So I think it just comes from, the confidence comes from doing it more and just communicating and sharing your ideas and getting that feedback. Okay, so if you do have any more questions, feel free to put them into the chat or into Slido. And now I'm going to hand it over to Hannah.
Cool. So I'm just going to drop a link into the chat for you guys, give you a link to the tutorial. And then I'll share my screen. So if you guys click on that link there, and if you get that up on your computer, I'm just going to share my screen. Cool. Sweet. So hopefully you guys can navigate to this page. Unfortunately, the link straight to the Google Colab was not working when I was clicking on it. So just to make sure it is working for you guys. If you navigate to this page here, and if you go to google.colab or colab.google, yeah, colab.research.google.com. Cool. And if you go to GitHub, sweet. So it's going to ask you to put in a link in there, and I'm going to show you which link to do. So you have two options today. Well, you have actually three options. I've got an answer notebook and I've got an activity notebook. So I'll be doing the tutorial and you can do it alongside with me. If you're not super comfortable with coding, if you just want to listen along, if you just click on this link here, and if you click on this notebook and grab the one with the answers, you grab that link, pop it into here. You can just run that. Or if you want to actually type in code and you feel like you want to do a little bit more today, then click on the activity notebook, just grab that link and pop it into here. So if you're stuck on that at all, please just reach out in the chat, and somebody else might, one of our team will be able to help you with that. But it's super simple. Grab the link.
Hey,
and
Hannah.
Then, yeah.
I just want to check with everybody. Can everybody see Hannah's screen?
Can you not see my screen? You might have to stop presenting.
Okay.
Sorry, thank you for letting me know. I can't see the chat.
I think I can.
I can see her screen, but I had to go into view options and then I had to select her screen instead of Mila's.
Okay.
I
can see your screen now, Hannah. So that makes me feel better.
Sorry, I didn't mean to keep talking for so long. I can't see anyone once I'm sharing the screen.
Okay. I think you're good.
Let me run that through again. So we'll start from the beginning. I'm going to pop in sorry, I'm struggling with Zoom once you go into share your screen. I'll take a step back. Cool. Sweet. Oh, Jenny's here as well. So thank you very much. Cool. So grab the repository, the one that you're interested in doing. I'm going to do the activity one today. And all you need to do is press the search, and it should pop up in Google Colab. And I'm keeping an eye on the chat now, so if you have any problems, I will hopefully see that. Cool. And so hopefully everyone has Google Colab up and running. So we're going to be doing a tutorial in Google Colab, and we're going to be using a few different tools today. Hopefully on your screens you can see this notebook. And we'll just start by sort of talking about what kind of data science problem you may solve when you one day become a data scientist, if that's what you're interested in doing. So one of the very common problems we do in data science, especially around marketing, is lead scoring. And it generally goes like this. So if we have, and we've got an amazing company called Zeducation, like Xero, but with X.
Hannah,
Oh,
sorry.
oh, you
Could
see
you
this top?
please
Okay.
check you're sharing the right screen?
Yeah, I think I was. Could you see it before?
I don't think so, no.
Right. Not sure. I'll try again. Sorry, I don't.
It's okay, just take your time. We've got
Yeah.
heaps of time.
Are you still? You're not sharing your screen anymore, are you?
I stopped sharing it.
Hopefully that should. Oh, okay. Sorry, it's because I dragged it across.
Nice. Okay.
Good.
We can see Google Colab.
Fantastic.
Okay.
Gosh, this is why I like Google Hangouts.
Yeah.
Okay, cool. Sorry, we'll get it right this time. So we have Google Colabs actually up and running. Let me know if you're having any trouble. So as I said before, we've got a lead scoring problem, and I've picked and making a company called The Education, and they provide online courses to industry professionals. So on any given day, there are many professionals who are interested in the course, and they're going to land on the website and they're going to browse for courses. When an individual lands on the website, if they sign up and fill up a form, then become a potential lead or potential customer for the website. And then once employees from the sales team will then contact the leads, and they might email or call them, and the goal is to get them to sign up for one of the courses they were interested in. When you have the process of a customer going from a lead to a paying customer, then we actually call that a conversion. So that's quite a common marketing data science problem about getting people to become paying subscribers. One quick way to sort of work out the problem that we're going to do today is called SCQA, and it's a common consulting technique. So we kind of start with a situation, and the situation is we've only got 38% of leads who go on to be contacted, actually go on to become a paying subscriber. And the big boss CEO has come in and he actually wants to grow the customer base by 20% of the next year. The complication is that the head of the sales and advertising department has a marketing budget, so he can increase advertising by 20%, but he hasn't been given the headcount to increase the sales team, so they can't get more people to make more sales calls, and they're already struggling to keep up with the amount of leads that come through already. So even though he could get more leads by increasing advertising, he wouldn't be able to keep up with, they wouldn't be able to keep up with all the new contacts coming through the funnel, coming through the sales department. And the department head knows that with a conversion rate of 38% means their team is calling people, and they're not calling people who are not interested and calling people who are not converted. And they know that they're wasting a lot of time on people who never intend to sign up. So we come to the question is, how can data science help to convert more leads with the same or even less amount of calls? And you as a data scientist may come up with the answer of a lead score model, and you can build a lead score model based on historical conversion data and help the sales team prioritize leads to form a better queue, to get the hottest leads at the top of the list and get the not so interested or coldest leads at the bottom of the list. And great, they love your idea, it gets approved. Now you need to decide what model you're going to build and what your data looks like. So that's a very brief introduction on the kind of data science scenario that you may find. Now we're going to talk just a little bit about the tools that we're using today. As I mentioned, we're working in Google Colab, and Google Colab today is hosting a Jupyter Notebook, and language we're using today is going to be Python. So as a very quick introduction to Python, you can click on this cell here, and you can do a very basic, and run anyway when it says that, run a very basic command like this one. And in the next cell, you can click on it, you can go print X and press play. So it's a little bit slow on Google Colab, so I'm just going to keep talking through. And you see it's printed out right there. Awesome. You can click in on the next cell. You can do another function called min X, and that gets the min of a list of 5. Awesome, that's 1, that makes sense. You click on the next cell, you can try the max of our list of X. And your option, you can press Control Enter, or you can press the little play button up there. Both will work. So in Python, we have things called functions, and they do operations on objects like X, which is a data frame. So here we've done the print function, which prints out a little array. We've done the min function, which finds the minimum of it, and we've done the max function, which does the max of it. And Jupyter Notebook, the reason we really like to use Jupyter Notebook as an interface to Python, which is exactly what it is, it's just a way to wrap it around the code, is because we can put these cells with text and with code together. There's a couple of things we can do. If you want to add a new code cell, you can click Code in the top corner and run over the code. If you want to add text cell, you can add a text cell. You go, this is a cell, and click out of that, and then you got that. So you can do manipulations in the same place. Cool. Now, the second thing we're going to do is we're going to import a few more packages to do some data science today. We just need a bit more functionality than's available in the Python base code. Python is an open source language, which means you don't have to pay to use it, which is why it's so popular among data scientists. And then people contribute extra functionality to it than comes with the base code. Our data scientist toolkit in Python generally includes the following packages. So we use something called NumPy for handling multi-dimensional arrays and matrices. We use something called Pandas for handling manipulation and analysis. We have some nice plotting functions called matplotlib and Xero, and I've just got a little bit of code there just to make everything nice. We don't need to worry about that too much. All you guys need to do is either click play or Control Enter to run that there. And just ignore that warning. It's just telling me that something's a little bit out of date. Cool. So like the min and the max and the print functions, import is just another function that we use, and it just gets us the packages that we're using. Cool. And I've aliased the packages as here using NP and pandas as PD. It just shortens the calls that we make to it. So it just makes code a little bit nicer, a little bit tidier. Cool, so we get to the fun part, we get to load in some data. So we're going to use functions from the pandas package to load in our data from a CSV. And then we're going to do some checks to make sure our data is loaded in correctly. So you may have looked at data in like an Excel spreadsheet, and what we've got here is super similar, but because our data is quite large, we can't actually view it all at once. So we do some manipulations on the data to try and find out what it looks like without looking at it exactly. We generally really like to look at the types of columns, the number of rows, and any duplicates or missing values, because that's going to give us a headache if we don't pick them up early on. So this here is a link to a CSV stored in my GitHub. Don't need to worry about too much about that, but we're just going to use the pandas function read.csv, pressing play, and it's going to read our data in. So what we're using today is called a data frame, and it's essentially like what you would see in a spreadsheet. It's just rows and it's columns, and it's just like a shape that holds data. And we have each row is an observation, and each column is values for that particular observation. And we can have a look at the rows and columns using the function shape. And just to know, I've called this data frame leaves.df. Yeah, cool. So we're going to call a function called leaves.df.shape. You may have noticed there's two different functions in Python. We won't get into today, but some of them you call up front and some of them you call at the end. And this one here, shape, is going to give us the number of rows. So we see that's 9,240, and then it's got 9 columns. So we can view the first 10 rows of our data frame using the function head. So you put leads.df.head, and then you can type in the number of rows you want to see. We just want to see 5. You just get 5 here. Awesome. So first off, we see the type of columns that we have. And we've got something called prospect ID, lead origin, lead source, total visits, total time, page views, specialization, occupation, and converted. So it very quickly looks like prospect ID is sort of an identifier or a GUID for our observations. And we have 1, 2, 3, 4, 5, 6, 7 different variables that are describing what happened. And converted looks like it's a column of interest. So this is what someone did, and this is if they're converted or not. It's also always good to look at the data loaded correctly all the way through. So we're going to use a function called tail. So exactly lead.df, leads.df, then tail, and 5. So we're going to look at the last rows. Cool. So we can see everything looks like it's loaded in correctly. Yeah, and with our 9,239 columns. Notice how this is a different number here. That's just because Python index starts at 0. So there is a total of 9,240 rows, but the first row is actually labeled 0. A little bit different if you're used to doing anything in R. Cool. So can we find out a little bit more about what these columns contain? One of my favorite functions is called describe. So the call is just leads.df and describe. Press Control Enter or the run button. Sweet. So this has actually returned all our continuous columns, so things that are continuous measurements from like 0 to infinity or negative infinity to infinity. And we've got the count of them, we've got the mean of them, we've got the standard deviation, and we've got some quartiles there. So this is a really good way to quickly summarize what each of these continuous variables looks like. Then we know that we have a few other variables like specialization, occupation, and maybe just those ones. And we want to, oh yeah, lead source and lead origin. If we also want to have a look at those, we just do leads.describe, but we include the parameter include.all, and then it gives us all of these. So you see some of these categories don't really make sense for categorical variables. We don't need a mean of something that's that contains just different groups. That's all good. It tells us how many different groups there are. So there's 4 different values for lead origin. There seems to be 11 different values for lead source. And we've got 17 different specializations and 4 different occupations. Cool. If we wanted to get all the different column names, we can run something called lead.df and then do the function column. And then we can see all our different column names. Now, if we want to select a single column, there's 2 different ways we can do that. We can call leads.df and we can do dot specialization. You can see that's given us the single column, and we see we've got some null values there. So we're going to come back to that. The second way you can do it is by putting the call inside there, like this. It will give the exact same result. And we can do this for any single column. We'll look at our converted column. All we need to do, didn't like that because I spelled it wrong. Ah, leads.df wasn't that one. This one. Cool. Or we can do, and it should might come up with prompts. You can just press tab or enter to get those. Just press enter to get any prompts that you see come up. It makes like coding easier. Sweet. So that's how we've selected different columns. We can do the same thing if we want to see 2 columns. We do exactly the same thing, but we're going to put it inside the extra set of brackets. Sweet. So we've got 2 columns there. And we could do it by, we wanted to look at 2 other ones, say converted and sweet. So that's how we'd subset the data. We can also apply functions over columns. So if I do leads.df dot converted, because I know this is made up of zeros and ones, if I apply the sum, cool, and it's actually given me how many people have converted out of that column. If we do the same thing, but we also use the shape variable, so leads.df shape, and I'm just taking the first value which we saw up here, which is again indexed at 0, and that one's 1, which gives us the length of the data frame. Cool, we've got the overall conversion rate for our data set, which is at 38%. Something else we like to look at is the number of duplicates. We see that returns a binary value. If we actually wanted to know how many duplicates we have, again, we can use the sum. Works as well. Note that there's actually two different ways to do this. You can go also sum dot duplicate. That works both ways. Doesn't work for all functions, just for some functions. Last thing is we'll look at the null values. So we're going to run is null over all columns. That's not super helpful because it's just returning yes and no for or false, true and false for all our values. But if we do this and combine it with some function, cool, we can see that all these columns have no null values except when it comes to specialization. So we might have to deal with data cleaning in that specialization column. So let's have a closer look at the specialization column. I'm using the same thing as before, leads.df.specialization to select the single column, and now I'm just going to apply a function to a single column using call value count. I'm going to run that. Cool. So we can see for all the different group levels in the specialization column, you can see what their counts are. And we can see that we have this value called select, which seems a little bit odd. It doesn't seem like a specialization like finance management or human resource management. And here we've got some null values. We can also try this with another column to have a look at that. So leads.df dot, then we'll look at occupation or value counts. And also look at, okay, cool, we've got 4 different labels for value counts. We've got unemployed, other, working professional, and student. Cool. So those are some really basic functions that we tend to do every single time we read in data. We have a good look through. We have a look at the number of rows, number of columns, any duplicates, any nulls, and what the levels and distribution of all the columns are. Now we get to the cool part, which is semi-cool part, which is data cleaning. So we know before that in our specialization column, we had 2 issues. One was this weird select value, and one was this null value. And we need to put in something that makes, when we come to model building, we have to put in something that makes sense, and it's not going to know how to deal with nulls. So what we're going to do is pretty much why select happened is because it was wasn't a good sheet. So when it didn't put in anything, it just said select. So that's essentially a null in our case. So what we're going to do is actually physically change the data frame. And we're going to say every time we see select, we're going to put in a null instead. So this is overriding the existing data frame because I'm renaming it here. And what's always good practice is every time you make a change to your data frame, just run it again. Cool. So we see that we now have a big group of nulls. We don't have any of the select ones before, which is exactly what we wanted. So now we have everything as nulls. We're going to go ahead and decide just to call this group of nulls other, obviously, because we're going to use some common sense here. And if they didn't select one of these, it was probably because they didn't have an option that suited their needs. So we're just going to put in the bucket that puts in everyone else who didn't quite fit these categories. Cool. And lastly, again, we're just going to run this cell just to look at the data once again. Fantastic. So we don't have any nulls anymore. We've just got a column other. Cool. So I cleaned a lot of this data already before I put it in here. Well, this is just one example of one column I had to clean. Usually you have a lot more data clean to do, but we're keeping this really quick and simple. And so we've just cleaned that one column, and now our data is pretty much ready to do some exploration. So we've loaded our data in, we've cleaned that data up. Now we want to have a good look at what the relationships are between the thing that we're interested in predicting, which is the conversion, and the other variables we have in the data set. And when we see in our data, we have prospect ID, which is the GUID or the unique identifier across each row. We've got converted, which is going to be our target variable, or also known as a response variable. And this is the thing we're interested in predicting. We also know this is binary, so it either happens or it doesn't. It's either a 0 or 1. And then we've got these mix of 7 categorical and continuous variables, and these are going to be our predictor variables, also called explanatory variables, feature variables, input variables, or independent variables, depending on what kind of field you come from. Essentially, we use the predictor variables to try and predict the target variable. So we want to have a really good idea, because we don't have such a big data set, it's kind of quite easy to have a look at the individual variables. When you get into really big data, this becomes a little bit harder. But we want to see if there's maybe any interesting relationships already existing in the data through some plotting and visualization. Cool. So what I'm going to do for our categorical variables, because they're grouped, we can look at box plots, or sorry, side-by-side bar plots of the rates of conversion in each one. So you've got the code here. Essentially, we're just setting up a plot, and we're going to use the Seaborn SNS count plot. And it's going to give us a count of lead origin versus converted. And just like that, we have a box plot of lead origin. Cool. So what we can see is that the API origin and the landing page submission origin, they tend to be the most popular ones, but their conversion rates probably sit about 50% each in comparison. So half the amount convert in API. And then we've got lead add form, and this one is a little bit smaller, but everyone seems to convert from this category, which is really interesting. And then the smallest category, which is lead import, which has some conversion, but not a lot of conversion. Cool. So what we can do, if you just copy that code, just Control-C, hop in the next one, and we'll have a look at lead source. You can copy out the entire code, or you can just type it out if you like, or you can just copy it over. But if we just change this one here, the lead source, we don't need to change anything else. We can run it. And now we've got a box plot for the lead source. So we can see that Bing doesn't seem to be popular for converters or non-converters. Direct traffic, Google, other seem to be the biggest categories, but don't have as many conversions as they have non-conversions. You see over here that the reference category has quite a lot more converters than it has non-converters. And same for the YouTube channel. And there's a group of unknown people as well that seem to have conversions, but we haven't quite known where they've come from. So that could be something we might want to follow up with later. And a quick look at specialization. Again, I'm just replacing that lead origin code with a specialization column. Cool. Okay, so there's a lot more categories in this one. We have a big group of other as well. So it seems to be, if you've told us where you come from, you've not just put other, you have actually a decent chance of converting, maybe about 50% compared to if you don't tell us at all. So that might be the main driver in terms of conversion in the data, if you actually fill something out. And lastly, let's have a quick look at occupation. I'm going to copy this. Sweet. Cool. So working professionals seem to have the highest proportion of converters to non-converters. And see that maybe students have a little bit less converters and non-converters, and same as unemployed, but unemployed is a much bigger category. Again, with other, if you're not really specifying if you're one of these, then you tend to have a much lower conversion rate. Cool, so very quickly, just had a quick look at the comparison of each of these variables with the response, which is converters. For our continuous variables, because it's like a measurement, we can't just look at box plots, we need to look at something that captures the distribution of the data. And so today we'll look at bar plots. I mean before, but today we're going to look at box plots. Now, for total visits, it's quite hard to see. It looks like those who convert might have a slightly higher median for total visits, and we've got this one outlier that's really, really high. Again, just copy the code, pop it over, and I'm going to take so this one's a little bit more interesting. See that the median for those who do convert is much higher, that line there, compared to those who don't convert. The range is about the same. So we have some non-converters who spend a lot of time on the page, but generally if you spend a lot of time on a page, it's more indicated that you are going to convert. So that could be quite a predictive variable there. And then we've got page views. It's the last one. So really not so much distinction between page views, between converters and non-converters. We've got this outlier here of this person who had a lot of page views and then end up converting. So that's kind of interesting. So we've got some idea what's going on. We're not entirely sure what's going to be the most predictive one. It looks like total time spent on page is probably the most important variable. What we can do now we've had a good look at our data and we've got a reasonable idea of what the shape of each variable is, what's contained in each variable, and how they relate to our response. We can now put them into a model. Now, we said before, our response variable is conversions and it's binary, it's either 0 or 1. So this is actually going to be a classification problem. So the type our response is, that actually defines what kind of problem and what kind of model we're going to build. And so what we're going to do is we're going to predict whether a leader will convert or not, the classification. So the first choice for many binary classification problems is a logistic regression. It's one of my favorites, mostly because I have a stats background, but I like it because of its simplicity and its interpretability. There are a few other options like random forest and neural networks, and they can provide better accuracy, but you kind of lose the simplicity of it. They tend to be larger models if you have to store or productionize anything. And with neural networks, they're more black box models and you don't exactly know what's going on. I think most of the time logistic regression actually does really well. So we tend to start with the most basic, easy model and then go from there. Cool. So the next part of model building is one of the most important parts, and that's called a testing training split. Essentially, we've got one big data frame of data, our leads.dev, but we need to be able to split this into two parts, one for training and one for testing. And this is because we need some data to train our model, but we also need to withhold some data so that we can test its accuracy on data it hasn't seen before. And doing this, we're kind of reflecting how our model might perform in real life. And we're checking that it's not really just fitting well to the data that's seen, it can actually do predictions on new data. And generally that split is between about 80% training and 20% testing. Depends how much data you have. If you don't have all the data, you might have 90% training, 10% testing, or it depends how long it takes to build your model as well. You might do a few different iterations depending on what you're trying to do. And there's a few other preparation steps we need to do. We need to remove the ID label because it's not actually a predictor. If you put it into a model, it's going to see a unique one for every single level, and there's not going to be any association there. It might make your model fit even worse. And we're also going to do a second thing, we're going to split out the tagging column. So that converted column, we're going to take it away from the the explanatory variables, and we're going to put them in two different data frames. And lastly, what we're going to do is for a categorical variable, so things like occupation with 4 different levels, we're going to create some dummy variables, and I'll show you what they look like in a second. But we need some more packages because we need some packages to do some model building. So what we're going to do is import something from sklearn, and this contains packages for training models. So it's going to have our logistic regression in it, and it's also going to help us do our testing and training split. So we're just going to click run on that. Cool. Second, what we're going to do is we're going to store our variables, so our converted variable, just in this Y column. Just going to assign it there. Cool. So that's stored. If we have a quick look, that's what it looks like there. So it's just keeping all our converted data in that one place. Cool. And so what we need to do in terms of creating dummy variables is because if we put in a categorical variable into a logistic regression, it's got 4 different groups, and in Python it doesn't like that. It doesn't know what to do with it. In R you can put it in straight away and it's fine, but what we need to do is split it out from one variable with 4 categories into 3 variables with 1 category, and I'll show you what that looks like. Sorry, I'm just going to steal this code here because I haven't put it in. Right, so here we've got now 4 different columns, and what this is saying is if you're a student, then yes or no. Are you an employee? Yes or no. Are you a working professional? Yes or no. So when all these are 0, then you're the fourth column, which I think was working for other. We can do it in two ways. You can create one for each, but if all these are 0, then you know you have to be one of them. So if we put in that there, we actually only need 3 columns. So if this is all 0, then you have to be other. There's no other option. So now we've got, instead of one variable with 4 options, we've got 3 columns there. And we're going to input in that model instead. So each of these are now binary values. And so what we're going to do, we're going to do the same subsetting that we did before, which is in here. So we're just going to get the categorical variables, which was lead origin, lead source, specialization, and occupation. And then we're going to run this function again, pd.getDummies, and we're going to assign it to an object called dummy1. Cool. And let's have a look at this dummy data frame. And we're going to use our function head again. Cool, so we see that we now have, instead of 4 columns, we have many columns, and each will have a value of 0 or 1. And this just means that now our logistic regression model knows how to deal with this, and it will be able to use these as predictors. Cool, so we still have continuous variables left, and they're stored in our leads.df with these 3 columns. So this is, again, we're just subsetting a data frame. We've got total visits, total time, and page views. I'm just grabbing a dummy data frame from above, and I'm using something called pd.concat, and it's just going to stick these 2 data frames together. And it's always a good idea to look at the data frame. Sweet. So now we've got one really, really long data frame, quite wide, but it's got all our variables ready for prediction. Cool. So last thing we need to do is create some testing and training sets. Now we've got the test train split from sklearn. What we put into it is predictor variables or explanatory variables in X, what are response variables and Y. I'm taking a test size of 0.2, so 20% in my test set. And the random state is just it sets the random seed, essentially, so we're all going to get the same random result. So it's a random sample into each, but let's just make sure it's reproducible and you're going to get exactly the same answer as me. And the actual output for test train split is actually 4 different things, and so I'm just assigning it in order there. So again, we'll just have a quick check that the dimensions of our data look about right. So let's have a look at x train, or x test shape, and then y test shape. Cool. So we see that it's got 35 columns, which makes sense. That's how many columns we should have up here. And it's got 20% of the observations, which is about 1,800. Let's have a quick check for training data as well. So we've got x.train and y.train. Cool. So that all looks about right. So there's just only rows in our y column just because it's 1 column. And then we see these both have the same amount of columns, and it looks about 8%, and that's 20%. Cool. So that's all loaded in correctly. Sweet. So after all these steps, we're now finally ready to fit our logistic regression model, and it's kind of underwhelming because it's actually only 2 lines of code. So all we have to do is run that. Cool. And then we have a model. You want to have a quick look at what's in that model object. It just kind of looks like that when you print it out, so we can see it's all logistic regression. Sweet as. Cool. So now we've built a model. We're going to do the second most important bit, which is actually evaluate how good our model is at predicting, because we can build a model, but if it's not very good at predicting the future, then it's not very useful to us. So what we're going to use is we're going to use this function called metrics.accuracy score. We're going to put in training data. Oh, sorry, I kind of skipped ahead. What I'm talking about here is that we have 2 ways we get an estimate. So I said before, we have our training data and our testing sample. So our training data is the data that our model has seen. So when we do accuracy based on sort of the internal or in-sample estimates, we call that the in-sample accuracy. And then when we test the model based on data, predicting data it hasn't seen before, we call it the out-of-sample estimate. So let's start with the in-sample. So I'm just using the y.train, so that was our training vector of conversions. And then using model.predict, which is just going to predict the x values, and it's going to be on our training data. Cool, so the in-sample accuracy was about 80%. And we're going to do exactly the same. So what we're going to do is we're going to predict for our new data, data it hasn't seen before, using model.predict. And this was our testing data, our x variables. And we're going to get the y's, which are going to be the prediction, using this function here. Cool, so we've got some predictive values. Cool, it's going to predict whether it's a 0 or 1, a conversion or not conversion. And what we can do is, again, look at that. Using metrics to accuracy score, we're going to use y.test, where we store the actual y values. And we're going to get our predicted values from this column here. Cool. So you can just copy this code and change this to y.test and this to x.test, or you can do it like this. Cool, so these look super similar. Usually what we find is that you have a lower accuracy on your outer sample and a higher accuracy on your in sample. It tends to overfit the data that you have, and that's why you want to evaluate it on data that hasn't seen before, and it tends to be a little bit lower. In this case, this was actually a little bit higher, sometimes just a random chance, depending on the data split. But overall, we've got 80% accuracy. So 80% tends to be the threshold for data science models, depending on how sure you need to be, is a big factor in how accurate your model needs to be. If you're dealing with life and death, you might need to be 99% accuracy, and that might take you maybe a couple months to build a model that accurate. If it's not so bad, if you get something wrong, then maybe 80% accuracy can be okay. Cool, and now we have this thing called a confusion matrix, which sounds super cool. But what we're actually going to see is how well it classified converters as converters and how well it classified non-converters as non-converters. It looks like this. So on each of the elements of the confusion matrix is these 4 things here. So we've got our true positives. So there's the amount of converters that actually got right, and that sits up here. We've got our true negatives. So there's a non-converters that our model got right. Which is, I don't know why it's showing different numbers here. Oh no, yeah, sorry, I've got different way down. This is the true positives, this is the true negatives. And then we've got the people that it thought were converters, but they actually weren't up here. And then we've got the people that thought they were negatives, but they weren't, and that's in there. So overall accuracy is just the amount that actually got right, which would be on the diagonals 989 plus 4, 476 over all of them should be. So that's how we get our overall accuracy metric, which is just this diagonal down there, so how we classify this right. But there's a few other things we're also interested in as well, which we can get from the confusion matrix, because we've got the true positives and we've got the true negatives, and we're kind of also interested what the proportions are of each. So when we think what we've got is sensitivity, and that's sort of the true positive rate. So of all those who actually are positives, what proportion of them actually got correctly identified as such in the model. Then on the flip side, then we have specificity, and it measures the proportion of actual negatives who got correctly identified as such. So this is how we'd calculate that. So sensitivity is the amount of true positives over all the actual positives. So those identified as true positives and false negatives. And then specificity is the true negatives over all the negatives. So the true negatives and the false positives. And we can see that our model's sensitivity is 0.66. So it kind of identified 66% of all positives correctly. but the specificity is a bit higher, so almost 90%. So our model is actually better at classifying people who don't convert as converters than it is at classifying people who do convert as converters. Did I say that right? Who don't convert as non-converters. That's what I meant. And that could be just because we have more converters than non-converters than we have converters, because the conversion rate was about 38%. So there might be just more data there, and so it can make that a little bit more prediction a little bit better. But we may want to change this around, because what we actually get for the predictions is probability. And so when I've made these predictions here, it's actually classifying everything that's more than 50% to be classed as a 1 and less than 50% as a 0. But depending on what's worse, so it could be, is misclassifying a non-converter as a converter and calling them by mistake, is that worse? If we had low specificity, or is misclassifying converter as a non-converter and not calling them, is that worse because we have low sensitivity? So we can actually move that threshold of 0.5% higher or lower, depending on how sure that we, where we want to push that needle, if we need to get more higher specificity or higher sensitivity. And I'm going to quickly show you guys our ROC curve. And it's sort of just showing the trade-off between sensitivity and specificity. So we could class everyone as a converter, and we'd actually have 100% sensitivity, but we'd make our specificity, which is 1 minus false positive rate, 0. So there's a trade-off between the two. So if it was really bad to not miss a call and you had to call every single person, then you'd want 100% sensitivity. You don't need to build a model if you need that. We kind of want to get, the idea is to be able to classify everyone really well. Cool. It's sort of a little bit complex idea, so I'm just going to briefly skip over that one. But cool, so you build a model and we've got 80% accuracy. We've got decent sensitivity and specificity. But obviously, the CEO and the department head, they're not going to understand that. How are you going to sort of convey to them that your model is better than what they're doing at the moment? So what I'm going to do, I'm just going to grab some probabilities that we predicted before, and I'm just going to put them in the data frame. So we look at that data frame. Cool, so I've got the actual values of our test data in one column and the predicted probabilities in the other column. So as we said before, anything that's over 0.5 is going to be a 1, and under 0.5 is a 0 when we classify. But what we actually can do is take this probability, and that's how likely they are to convert. So what we can do with this is we can order people based on how likely they are to convert to how the least likely to convert. And we can do that and sort of take 10% cuts. So I'm going to take the top most likely people, 10%, and then the next 10%, and then the next 10% till we get the bottom 10%. And that's what this function is going to do here. Oh, and I'm just going to use my trusty value counts to have a look at this. Cool, so now we have 10 or 9 different buckets, which is what we wanted. This is a little bit off in Python, it's just how it's broken everybody up, but this here is the highest decile with the most converters, and this is the bottom decile here. And I'm just going to do some quick calculations to get that all into one data frame. And I'm going to quickly show you what I've done here. So this is a decile, they're not named particularly well, but just imagine sort of top bottom 10% to all the way to the top 10%. So this is the count of converters in the top decile. This is the count of all people in that decile. This is the probability of conversion, so 168 over 185. So we see we've got really high conversion rate in that top 10% decile. And this here, this is old. This is just saying what the conversion rate if you didn't do anything differently. So you're just taking a random sample, which is what they were doing before, and that's just 38% times 185. And we've done that for every single decile. We've got the number of conversions in each decile, and we can see they're all pretty much equally sized. And we're going to do something called a waterfall plot. It's going to look like this. And I am skipping over this because the code is getting a little bit more complex, and I just kind of want to show you the ideas rather than getting into the individual code. But you guys can have a look and play around with it later if you like. But what this waterfall plot is showing is the blue bars are in each decile. So 1 here is the top decile, 10 here is the bottom decile. How many converters we have in each in the blue, how many non-converters we have in each in the blue. And so we've got more converters in the top deciles, less converters in the bottom deciles, which is exactly what we wanted our model to do. We wanted it to rank people based on how likely they are to convert. And this red line here, this red line is how many conversions you get in each one if you keep the whole way through. And we can see it can't discriminate between deciles. It's just saying if you called 10% of the customers, you'd get this amount of conversions. So what we want to communicate is that if we contact the top 10% of customers, they're 98% likely to convert. So they should always be at the top of the queue for the salespeople because they're always going to convert. The middle percent of leads, they might still convert, but they're less likely. So they're definitely less of a priority. Put them after the top leads. And we've got this bottom 10%, 30% here, and they're really unlikely to convert. So you wouldn't even need to call them because it would probably be a waste of time. Now, one fun idea is, can you work out if those in the top decile who might convert without even needing a sales call? But that's a little bit more complicated. So I'm going to leave that as food for thought. One option could be A/B testing for that. Cool. And then the last plot, and I think most impressive plot to show to your CEOs, is the lift plot. And this is showing how much better our model is going to perform compared to the existing method or no method. So this red line here is if you pick people at random. Of course, if you call 10% of the customers, you're going to get 10% of the conversions. However, with this one here, if we show the top 10% of leads, we're actually going to capture 24% of all conversions. And we only need to call 70% of leads, of our top 70%, and we've actually captured 95% of all conversions. So there's a bottom 30% of people that we don't even need to bother calling, and suddenly we've freed up a whole other resource of our sales team, and we can get more conversions and a higher conversion rate by making even less calls. So all we need to do is call people in the right order, and we're going to drastically increase our conversion rate. Cool. So there's a few different steps. Data science is a very iterative process. You might want to try and get higher accuracy by trying a different model. You can transform your variables, maybe square them, log them, play around with them. You can try including and excluding different data and see if it improves model performance. You can train some hyperparameters. So that's changing things within your model. Not so much to do with logistic regression, but you can in neural networks and random forests, quite a few hyperparameters. You can also look at adding new data. So add the data that you haven't got before. But it's an iterative process. You'll keep going until you've got the level of accuracy that you've required. Sweet. So that's the tutorial for today. I'll hand it back over to Mila to wrap up.
Cool. Thank you so much. I just wanted to just point out that even if you followed along, that's really cool, and I hope that you enjoyed that and you can try out some other tutorials online or find some other data sets to play around with. And if you didn't, then that's totally cool as well. I hope that you can still see how essentially why businesses are hiring so many more data scientists or collecting data to improve their businesses, because the data there will really dramatically can help how much time the business is spending on calling the right customers and making sure that their employees are spending their time where it's really going to be most impactful. And that's where the data scientists can really help. And this can apply to a range of different things. So I'm just going to share screen again, just so that we can wrap up. Cool. Can you see my screen? I hope so. So just as a wrap up, data science is truly for everybody. There's so many online resources that you can pick up today and start learning these skills. And there's so many data sets as well that you can play around with. For me, that's honestly how I really got interested in data science. I started just to be curious about what's out there and to try and start to problem solve with data. So to sum it up, like, remember that data science is about finding patterns about the world and trying to make predictions about it so that we can anticipate future needs, which I think is really applicable to any industry that you might be interested in. And it's a very accessible and really fun profession for everybody to get into. It's really calling in for people that are more about, I guess, problem solvers than just purely people that want to code or just do data analysis. From my experience, there's been, I had a few friends that have converted from quite creative backgrounds and they never thought that data science could be a career for them because they felt like they needed to learn how to code a lot and it was just like, you know, a scary thing to do. But they found that they had a really great time doing it and they just needed to have some guidance to get them started. And after that, they were off on their journey. So to wrap up, I have a few more links here. There's honestly so much materials online, and check with Victoria University about how they might be able to support you in learning about statistics and coding and maybe finding a community out there. Stats New Zealand also has really good data sets that you can play around with. And I think it's really nice that we can have an ability to learn more about New Zealand and what's happening here. So that's about it. Thank you for coming. I'm just going to quickly check some questions that have popped up. So there's a question maybe Hannah you could answer. It's asking, would you recommend taking high level, like past second year statistic papers for data science?
I might be slightly biased because I'm currently doing my master's in statistics. So I did postgrad and then I came back for more. I think it depends on the type of data scientist that you want to be and the kind of problems that you want to solve. And also how you learn as well. So I quite enjoy learning from statistics from a very academic standpoint. And because I am more a statistician than I am a data scientist, I find that statistics and that theory is much easier to learn at university. Some people are much more applied and do much more machine learning and data engineering. And I find that software developers can find that transition a little bit easier, but they don't tend to do as much math, say, or statistics as I do. So depends what you want to learn, depends what you want to get into. I might still go and do a PhD just because that's the kind of thing that interests me and that's what I want to apply to my career. So there's many different pathways. I would say do more statistics. I think statistics is super powerful. If you're leaning more towards data science and rather than machine learning engineering, which we touched on, I think knowing more statistics can be really, really powerful.
Cool, thank you. I would agree with that. I studied mostly computer science and I took stats was my minor, but in some ways I wish I did more statistics, and part of like my learning plan, so like things I'm trying to upskill myself in, is actually more statistics and math. It's really is like foundational for understanding deeper about the different functions that you're going to use. For people that are just starting to learn about data science, I think you should just try and keep it as simple as possible and just try and analyze the data set and learn as you go. You know, you don't need to start learning all of statistics in one go to become a data scientist. You just need to start there. And yeah, probably higher statistic courses will help along the way, but it's up to you.
And just to add to that, Mila, you can come back for more. So
yeah, I probably will.
I'm only just finishing my master's now, and I found that I wanted to learn more, and I wanted to know how to solve more problems. So I decided it was time for me to come back and to do a second postgrad. But this time I did it part-time, which is fun. So if you're not sure, if you don't know what you need to learn, probably you can finish university, find the job, and then come back. And studying part-time is actually a lot more fun than being a student full-time. So
yeah, that's funny enough, I was researching some courses that I could do post-grad in stats part-time. Yeah. There's another we should chat more then. There's another question about is there any tips for applying for jobs, writing CVs and resumes? I think if you're just starting out as a graduate and maybe you have a little bit of experience working in industry, one of the main things that the employees are going to be noticing in your interview or in your CV is more about like your personality, your characteristics, those soft skills that we talked about. They know that, like most companies know that if you don't have like a certain like programming language or technology that that they're using online in their business, they're able to teach you how to do that. It's much easier to train somebody on the job than to expect everybody to have some level of experience in it. It's much harder to teach somebody those soft skills. So it's much harder to teach somebody how to communicate more effectively or how to get them to be more curious. So if you can show those competencies in your CV or in a job interview, it's going to increase your chances of getting hired. Also, just asking questions. So if you're going to apply for a company that's hiring for a data scientist, data analyst, you can just send them an email or just asking them, being like, hey, could you give me any advice about what you're looking for? Often people are just wanting to get to know you better. That's it. So as long as your CV is showing your true self, that's going to be the best thing in there. Just show why you're interested in there, and the rest will kind of follow along. Does anybody else want to give advice?
So another thing to add to that for any CV, not just data science, would be to add examples of where you've shown something, because often that holds a lot more weight than just saying I have teamwork skills or I have communication skills. If you can show an example of where you've used that skill, that will definitely help you a lot.
Yeah, that's for sure. When I was applying for internships and like my first jobs, I didn't have like heaps of personal projects because university is full time and it was already really busy, and still like there was a whole load of us that still got jobs even though we were in the same boat. So I don't know, don't feel like you have to go bend over backwards and have expectations. I think in New Zealand and Australia there's a lot kind of more, people want to employ you for the person that you are instead of employing somebody that looks great on a piece of paper. There's another question about resources online. So one of the things about online resources is that they will teach you how the coding skills, some of the statistical skills, maybe machine learning, like basics of machine learning. But it's really worthwhile to understand or keep note of like the things that you're curious about or you want to learn more, and go back to like the core roots of that profession or that field. So there's like Coursera and DataCamp and Code Academy. They all have like interactive online workshops that often I think you can get it for free. There's also, if you just search on Google, some free data sets or tutorials, you could find heaps of examples as well. So these are really good starting points to just kind of get a feel about what you might be curious about, what you want to learn more about. And then I would recommend to go back and do more thorough research in that specific field or that specific skill. There's also, information is beautiful. If you're into data visualization, it's like the best database website out there. The theme is amazing at communicating different data styles, and it's a really good website to go for inspiration. the other little thing I drew in here in the bottom, in the middle, is just to experiment. So you're really going to learn a lot if you just try it out. The code isn't going to bite back if you make a mistake. It will probably throw an error and tell you that something is wrong. And Stack Overflow is your community of people to reach out for help. But just try it out. Like, nothing bad's going to happen. And you should try and see what you find it fun. There's different types of data sets that you might be interested in. So just find a data set that you're curious about. There's whole data sets just about dogs, you know, like, so just start somewhere where it's fun. You could start picking up the skills and then move on to something that you want to focus on. There's a question about us, what our degrees are, and what kind of courses we did at uni. I can quickly go first. I started studying software engineering at Vic, and then halfway through, I got an internship at a SaaS company in Wellington called Optimal Workshop, and I was a Rails developer for them for several years. And with my university, I knew that I wanted to actually study more math and statistics, so I changed degrees to computer science. That was going to let me have more science papers, and so I picked up more statistics, and one of my years was essentially all about math and statistics. And then I worked as a software engineer for a few years, and my job at Optimal Workshop started to shift more into data science. So then I chose to change my job into becoming a data scientist, and by the end of working there, I was the lead data scientist, which for a small company might not be like a huge achievement, but it was still a really big personal achievement to get there. And I learned to do a lot of different things around data science, things that improve the company. Does anybody else want to share their kind of journey to getting where they are?
I can share mine. So I did maths and stats in my undergrad at Auckland University. I did a honours postgrad in stats, and then last year I went back and started my masters in statistics. So I'm definitely more in the statistics camp of data science, and I enjoy, so I'm currently doing research in Bayesian statistics and the application around industry and marketing at the moment.
Cool. I need to see the chat and see if there's anything else in there. I have no idea where the chat went.
There's one question right up the top of Slido. I don't know if you answered it, Mila?
Yeah, I have answered that during the presentation. Sorry, I can't really find my chat anymore.
I couldn't see any more questions that I saw.
Cool. I guess we should wrap it up here then. Thanks for coming. If you see us, I don't know, at meetups or online, LinkedIn, just feel free. You can definitely send me a message on LinkedIn if you want to ask more questions. And we hope this was useful and inspired a few of you to keep learning. And thank you so much. Okay, bye.